All right, so I'm going to call this 8.2 star, meaning that it comes in after Unit 8.2. I'm just going to do some questions. These were some questions that folks asked me today during class, and some questions that they didn't, but that I think relate. I'm going to do two questions of the type where you want to find the general form when the first term is unknown. One will be a geometric sequence, the other will be arithmetic. And then after that, I'm going to do some questions where we come up with sigma notation for series. Those are from exercise 1C. I'm going to do all of number 2. And I'm going to try to point to some tips and tricks as I go. Okay, so first of all, two questions where we're looking for the general form where U1 is unknown. Quick review. The general form, of course, we have a general form of arithmetic sequences and a general form of geometric, whatever the other one is, I didn't say. So the general form of arithmetic sequences is that the general term is the first term plus the common difference times n minus 1. And the general form of geometric sequences is the nth term equals the first term times the common ratio to the exponent n minus 1. Okay, and more details of those can be found in the previous videos, but let's just have them there. Okay, here's my first example. Suppose we have a geometric sequence. So I'm just going to write geometric sequence like that. Suppose we know that term U5 is 40. Suppose we know that term U9 is 1562.5. And suppose we're asked to find, let's just say UN in general, and then maybe U1. Okay. So what we want to do here is we have U1, U2, U3, U4, U5 is 40, U6, U7, U8, U9 is 1562.5, and on we go. Okay, it's really important that we know how many jumps there are between the two known term values. Okay, and by jumps I mean how many times do we multiply by r to get to the next one. So we multiply by r to get to the 6th term, we multiply by r to get to the 7th term, we multiply by r to get to the 8th term, and we multiply by r to get to the 9th term. So to get from the first one to the second one, we have 4 jumps. Okay, and this is also the same as the term number here minus the term number here. So 9 minus 5 is 4. The number of jumps between two spots is just the subtraction of those two. Okay. Now you want to be able to do the subtraction because you could have a question where instead of a 5 and a 9, which are fairly nice, you have a 51 and a 99. You don't want to be counting all the positions between 51 and 99, right? So there you go, 99 minus 51 to see how many jumps there are. So that's the first part. Now, why do I want to see how many jumps there are? Well, because if I know how many jumps there are, I can set up an equation to determine r. And that, of course, will get part of this equation here for me. That's a critical component. So to set up the equation, basically I could say, look, if I start at 40 and times by r 4 times, I end up here. In other words, 40 times r times r times r times r, r to the 4th, equals 1562.5. So here now, I have one equation, one unknown, so I could solve for r. Okay? So let's do it. R to the 4th is going to be this number here divided by 40. Let me just pull up a calculator for you to see there. So I have 1,562.5 divided by 40. I get 39.0625. And then I'm going to take the fourth root. And now me personally, I just like to use the property that the fourth root is the same thing as to the exponent of 1/4. I find that easier. So here I'm going to now just go to the exponent of 0.25 equals. Okay, or you could do the fourth root if you feel more comfortable with that. So we get r equals 2.5. Okay, so this is really good. We've got r. Now the next thing you need to do is say, all right, I've got r right here, but I still don't know the first term. Okay, so we've got to do some additional work to get the first term. You know, so far my equation looks like this. un equals u1 times 2.5 to the n minus 1, but I still have two unknowns there. I'm not done. So what I'm going to do is I'm going to take either one of these numbers, either the 40 or the 1,562. Obviously, I'm going to pick the 40 because it's smaller and easier to work with. I'm going to take that, and I know that it is term number 5. So what I'll do is right here, I will put 40, and it's term number 5, so n is 5. So I'm going to get to put 5 right there. Okay, so I get 40 equals u1 times 2.5 to the 5 minus 1, because it's term number 5. And now I have one equation, one unknown, and I'll be able to solve for u1. Okay, so bringing the calculator back up, I have 2.5 to the exponent of 4. This 5 minus 1 is 4. Okay, that's 39.0625. 40 divided by that. In fact, what I'm going to do is I go 40 divided by, instead of trying to remember the 39, I'll just calculate in my brackets here, 2.5 to the exponent of 4, close my brackets, there's the 39, equals 1.024. So u1 is 1.024. Now I have the general form for this geometric sequence, because that's my first term, that's my r. There we are. Okay, so now I've got it, and now I can answer any question I may want. The one we were given was find u100. What's the 100th term? Fine, I can do that. u100 is 1.024 times 2.5 to the 100 minus 1. Bring up my calculator. All I have to do here is go 2.5 to the exponent of 99, some ridiculously huge thing, times 1.024, some still ridiculously huge thing. I'm obviously not going to put down all those digits, but let's just do it in scientific notation. It's approximately, what do we have here now? Let's just say 2.55 times 10 to the 39. Okay, so that's one. Now, let me do another example, very similar, but this time we'll be dealing with an arithmetic sequence. Okay, so I made up a question that goes like this. We have an arithmetic sequence. We're told that it's arithmetic. We have that U7 is 39. We have that U15 is 60.6. And we're asked once again to find the general term, un, and we're also asked to find u of 100. Why not? Okay, so here now is the same thing. I'm thinking, how many jumps are there between u7 and u15? 8 jumps. Okay, but instead of multiplying by r each time, this time I'm adding d each time. Okay, so now I don't have to actually put this out, but I'm going to put it out just for the sake of illustration. 1, 2, 3, 4, 5, 6 terms, and then the 7th one is 39. 8, 9, 10, 11, 12, 13, 14, and then the 15th one is 60.6. And you can see that the number of jumps is going to be 15 minus 7. It's going to be 8 jumps. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 jumps. So we are adding D each time. So if I'm adding D 8 times, I'm adding 8D, right? I have 39, and I'm adding D 8 times. I'm adding 8D, and I'm ending up with 60.6. So I've got an equation here now where I can solve for D. Just like the first step with the geometric was to set up an equation where I can find the common ratio. I'm multiplying by R 4 times. Well, here I'm adding D 8 times. Okay, and so here now I'll be able to find my common ratio. So let's just pull up the calculator. Oh, is it there? Oh, my calculator's missing. Okay, hopefully that's working. So so I'll subtract 39 on both sides. So 8D is 60.6 minus 39. And then I'll divide both sides by 8 so that I get D is 2.7. Okay, great. I've got D. So I know that my general form is UN equals U1 plus D onto n minus 1, and now I have D. Okay, so I have UN is U1 plus 2.7 onto n minus 1. But the problem is, once again, I don't have U1. Okay, so I have to go find it. And once again, just like before, the way I'm going to find it is I'm going to pick one of the two numbers I know, 39 or 60.6, doesn't matter which one, but I'll pick the easier one, 39. And what I'm going to do with that 39 is I'm going to use this as the general term. This is my UN, and my N is 7. So I'm going to take the general term that I have so far, and I say, look, 39 is the first term plus 2.7 times 7 minus 1, because I'm at the 7th term. N is 7. And here now I have one equation, one unknown, so I'll be able to solve for U1. Okay, if I go 2.7 times 7 minus 1, that's 2.7 times 6. 2.7 times 6, 16.2. Subtract that from both sides, and, well, I'll just subtract 39 and then change the sign. So I get 22.8. U1 equals 22.8. Now I have my general formula. I have that UN equals 22.8 plus 2.7 n minus 1. Okay, some people like to distribute the 2.7 and collect some like terms here. Watch out for that. That could happen, right? So we could have 2.7n plus, what would that be when we subtract off 2.7? 20.1, right? That's an alternative representation. Other people like to just leave it alone. So now I can answer, well, what is term 100? Well, we just go 22.8 plus 2.7 times 100 minus 1 and bring up the calculator. 100 minus 1 is obviously 99, so 99 times 2.7. There we have it. We add on our 22.8, and it's 290.1, okay? So here we have 290.1. Okay, so there's two examples. Hopefully you find this helpful. Now, one thing I want to point out, if you're seeing how many jumps there are between two numbers, you subtract their positions. This is a little bit different from when we said, well, how many terms are there in sigma notation, where you have as starting point and an ending point. Because here, this isn't how many jumps, this is how many numbers including both the 10 and the 5. Okay, so if I have just that, let's say, I'm going to have, 6 terms. Here, I have 10 minus 5 plus 1 equals 6 terms. And you can see them by evaluating. This would be 5, then increase to 6, 7, 8, 9, 10 is where we stop. And we have 1, 2, 3, 4, 5, 6 terms. Okay. So the number of jumps, you just subtract the 2 positions. The number of terms here, where you include both endpoints, you have to add that 1. Okay. So now I want to do some questions where we have series. We have sums, basically, and we want to put them into sigma notation. So all of these questions are coming from page 12 in the textbook, exercise 1C, number 2. Okay. So I'm going to start with A. A is 4 plus 16 plus 64 plus 256 plus ... Okay, going on infinitely. Summation notation. All right. So what I need to do is I need to figure out, first of all, figure out what the pattern is. And in particular, I need to figure out, can I write every single term in terms of one variable where that variable increases by 1 each time? But first, just try to see if you can get it in terms of one variable that increases, or even decreases for that matter, and then you can fix it up. So 4, 16, 64, 256. What do they all have in common? Well, what jumps out at me is that they're all powers of 4. Okay? You might start with they're all multiples of 4. You might start with they're all multiples of 2. Those are good places to start. But if you look at them more, you see that they're all power, whoops, not to the 0, to the 1. They're all powers of 4. Oh, n'importe quoi. And once you see that, then you think, okay, how can I express each of these terms in terms of something that's constant, unchanging, and in terms of something that is changing? Well, you can see I just did it there for you. The base isn't changing. So in my summation notation, the base won't change. The exponent is changing, so the exponent needs a variable. We could use I, J, N. I'm going to use X this time. So the exponent is changing. And then, depending on the question, you may have to massage it a little bit so that this changing part is changing by 1 each time. Here is obviously changing by 1, so there's not much that I have to do. I say that X starts at 1, and it never ends, actually. I was about to say ends at 4, but no, this is going on forever. So you can just put it like that, or I like to put an infinity on top, just to emphasize that it's going on forever. Okay, that would be A. B. We have 3/4 plus 4/5 plus 5/6. Stop. Okay. So I have to think, what's the pattern? And if you look at it for a bit, you may say, oh, the pattern is the numerator is going up by 1 each time. The denominator is going up by 1 each time. What's not changing? Well, they're all fractions. So in my summation notation, what's not changing? The fact it's a fraction. What is changing? Well, the numerator is changing and the denominator is changing. So both the numerator and the denominator will need to be represented using a variable or an expression. Okay. How is the numerator changing? Well, it's going up by 1 each time. That's good. That's what we want. We want it to be going up by 1 each time because that's how the summation notation works. Where does it start? 3. Okay, let's keep things simple and say we're going to start at 3. If we start at 3, this can just be an x. And then it will go to 4. Good, that gives us the next one. Then it will go to 5. Good, that gives us the last one. So I better put a 5 up here to say we stop there. Okay, so the pink part is done. Now, the next question, though, is how do we get the denominator? I can't just put an x because that would mean that we start with a 3. And I don't want to start with a 3. I want to start with a 4. Well, what expression could I put here so that I start with a 4? Right? I want this to be a 4. What expression should it be? I want it to be a 4. X is starting as a 3. So what do I need to do? Well, I need to add 1. If I add 1 to my x, I'll get to 4. In other words, I'm going to put x plus 1. If x is 3, I get 3 plus 1, that's 4. Then 3 goes up to 4. 4 plus 1 is 5. Perfect. Then x becomes a 5. 5 plus 1 is 6. Perfect. We've got this covered. Okay? And it's a very good idea, especially as you're practicing these, to try it out. So this summation notation says I put a 3 where I have the x's. 3 over 3 plus 1, that's 3 over 4. Good. Then I increase the 3 to a 4, so then I have 4 over 4 plus 1, that's 4 over 5. Good. Then I increase it from a 4 to a 5, I have 5 over 5 plus 1, that's 5 over 6. Good. Okay, so this works. Now, I didn't have to start at 3. Okay, I could have started somewhere else. I could have said, I want to start at 1 because I like to start at 1. No problem. So here I go. X equals 1. Now I don't want this to be just x anymore because then it would be a 1. I want it to be a 3. What do I have to do? I add 2. Okay, so when x is 1, I get 1 plus 2 is 3. That gives me this numerator. I want a denominator of 4. Well, then I better have x plus 3 down here. How far do I want to go? Well, I have 1, 2, 3 terms. So this should be a 3, right? 3 minus 1 plus 1 is 3. So this gives us 3 terms. And now let's try it out. Put in the 1, I get 1 plus 2 over 1 plus 3, plus, put in a 2, I get 2 plus 2 over 2 plus 3, plus, put in a 3, I get 3 plus 2 over 3 plus 3. That's going to give me 3 over 4 plus 4 over 5 plus 5 over 6. Bingo. Okay, so that's another expression. And if you think about it, how many different expressions are there in summation notation for this? Well, here's one where we start with a 3. Here's one where we start with a 1. Do you think it's possible to do one where we start with a 2? Yeah, it is. That might be a good exercise. One with a 4? Yeah. With a 0? Yeah. There's, in fact, infinitely many equivalent summation notations to get that series. Okay, that's B. C. C is -1 plus 1/2 minus 1/3 plus 1/4 minus ... plus 1 over 100. Okay. So I can see that there are 100 terms in this sequence. In this series. The first thing that jumps out at me is this alternating sign business. Subtracting, adding, subtracting, adding, subtracting, adding, subtracting, adding. To get an alternating sign, I want, well, I want, well, I'll just show you what I want. How about that, Mr. Jones? Just show us what you want. To get an alternating sign in summation notation, here's the trick. And once you get used to this, you'll see this piece as being for the express purpose of alternating a sign. You get a -1, and then you raise it to whatever your index is. So that if my index here is a 1, I get -1 to the 1, which is -1. Boom. Then when it becomes a 2, I get -1 squared, but -1 times -1 is +1. Boom. Then when it's a 3, well, -1 to an odd exponent is a -1 again. Boom. When it's a 4, positive. 5, negative, and so on. Okay? So this expression will give you an alternating sign. Now, sometimes you need to adjust it with a +1 here, for example, or other adjustments to make the negative come in where you want it. But this is the form, having a -1 raised to the variable that you're using here as your index. Okay, so that's one thing. What's happening just with the numbers? Well, this is 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 100. Okay, and again, I'm going to say, what is staying the same? What is changing? What's staying the same? Well, this is staying the same. The fraction is staying the same. And what's changing? The denominator. So the things that are staying the same need to just be written. The things that are changing need a variable. In this case, I'm just going to have an x. Because when it's 1, I get the first one. When it's 2, I get the second one. 3, the third one, and so on. And this is going to go up to 100. And double check. You can plug in 1, plug in 2, plug in 3, plug in 4, double check it's working out. This one's good. Okay, D. This is an interesting one. We have -2 or 0 minus 2 minus 2 minus 2 minus 2 minus 2 minus 2 minus 2, blah, 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 blah. I think there's 8 of them. Well, this is the same as -2 plus -2 plus -2 plus -2 plus, well, I'll finish it off, 8 of them. Okay. I'm just adding -2 8 times with summation notation. Okay? Same thing. What is constant? What is changing? Constant, -2. Changing, nothing. Nothing is changing, so we don't really need to put our index variable anywhere. What's staying the same? -2. What's changing? Nothing. So this would do it, right? Think about it. This just says x is 1, we get a -2, plus increase x to 2, we get a -2, plus increase x to 3, oh, we get a -2 again, plus increase x to 4, another -2, increase x to 5, increase x to 6, increase x to 7, increase x to 8, and we're done. Okay, and we've added -2 8 times. That's it. E. 5 plus 10 plus 17 plus 26 plus ... Now this one's interesting. Well, they're all interesting, but this one may cause a little bit more grief. And I'm going to give you a little bit of a tip for questions like this. You might start by saying, is this an arithmetic sequence? Well, let's see. We're adding 5. We're adding 7. We're adding 9. No. But the next part is, look, we've got an arithmetic sequence for what we're adding each time. You see that? This is a constant 2. But it's sort of like a second order arithmetic sequence, if you like the expression. It's not an arithmetic sequence. The blue one isn't, but the red one is. So, what does this mean? Well, I'm just going to tell you, and when we do calculus, I can show you why. When you have this kind of situation where the thing that you're changing each time itself changes by a constant, it means that you're going to have an x squared. Okay? Why? I'll show you with calculus later. Probably in, I don't know, September or October. So I've got to think, can I get these numbers with something related to squaring? Pause the video and see if you could figure that out. What related to squaring? Okay, so look, each one is a number squared plus 1, right? 5 is 2 squared plus 1. 10 is 3 squared plus 1. 17, 4 squared plus 1. 26, 5 squared plus 1. Huh? Is that neat? So, what is changing? What is staying the same? What's staying the same? Well, the plus 1. What else is staying the same? The squaring. What is changing? The base. Okay, so what's staying the same has to be written down there. So a squared and a plus 1. What is changing is the base. That's what I'll make my x. And let's keep things nice and simple. X will be 2. 2, 3, 4, 5. Boom. That works. Now, maybe you'd like another expression. Maybe you don't want it to start at 2. Let me show you something. Let's suppose we want it to start at 1. Okay, and I'll use another variable, n. I want to relate x and n. Well, look at the first part. Imagine that we have a 2 and a 1. What do I have to do to make these equal? Well, obviously, I need to add 1 to the n. If I add 1 to the n, I get to x, right? If I add 1 to n, I get to x. So x equals n plus 1. Or equivalently, n equals x minus 1. Okay? So, here now, what's constant? The plus 1. What else is constant? The squared. What changes? The x. But x is n plus 1. So I'm going to put an n plus 1 here. Okay, I've now successfully changed from, well, it shouldn't be a 5, this goes on infinitely. I've successfully changed from one variable index to another. Okay, F. Last one here. 49m to the 6 plus 64m to the 7 plus 81m to the 8. And the pattern continues all the way to 121m to the 10. What's changing? What's staying the same? What's the pattern? Well, the exponent is going up by 1 each time. Fine. M is the same each time. Whoops. Fine. What's significant about 49, 64, 81, 121? Well, these are perfect squares. Okay, this is 7 squared, 8 squared, 9 squared, and so on. So in fact, the square is staying the same. Right? So I have 7 squared m to the 6 plus 8 squared m to the 7 plus 9 squared m to the 8, and so on. The m is constant, the squared is constant. What's changing? This exponent, this base. So, in my summation notation, I need the squared and the m to be there, because they're constant. Where should I start? Well, maybe I'll start at 6. That makes it easy for the exponents. So then my exponent here is just x. So the first one is a 6, the next one is a 7, the next one is an 8. That's good, all the way up to the last one is a 10. Great. How about the base? How can I express the first term, 7, in terms of 6? Well, you add 1. So I'm going to go x plus 1. Now my first one is 6 plus 1, 7 squared, perfect. My next one, 6 would then become a 7, 7 plus 1, 8 squared, perfect. My next one would then become an 8, 8 plus 1, 9 squared, perfect. I've got it, okay? And you can go through and see if this is correct. Again, now let's suppose I wanted to do it with starting at 1 or maybe even starting at 0 for some reason, okay? Computer science, there's a reason why you might want to start at 0. I just need to change this a little bit. Focus in on the first value. Okay, 6 equals 0 plus what? Well, plus 6, obviously. So x equals n plus 6. Right? Isn't that true? 0 plus 6 gives me 6. N plus 6 gives me x. So everywhere I see an x, I replace it with an n plus 6. So I'm going to have n plus 6 plus 1 squared m to the n plus 6. Or in other words, n plus 7 squared m to the n plus 6. N starting at 0. And going to where? Well, x is 10 when we stop. X is 10 when we stop. So what does n have to be when we stop? Well, subtract 6 on both sides, 4. And another way to double check that is we have the same number of terms. 10 minus 6 plus 1 gives me 5 terms. 4 minus 0 plus 1 also gives me 5 terms. Okay, so that checks out. And if you want, try expanding this and see if this really does give you the right series. All right, that's it for now. Happy math!